So in this lecture, we're going to discuss what's meant by this idea of free energy when we talk about it from a chemistry perspective. And so we can recall, when we talk about free energy, we're talking about our Gibbs free energy, which is otherwise known as delta G. All right? And we can define this Gibbs free energy as this is the maximum amount of energy available to do work. Oops. Mathematically, we could write that as delta G is then equal to work max. And so, and all we're really saying here, when we think about what this really is we're saying when we get a value of delta G, if that delta G is spontaneous, the energy that we get out, that negative value of delta G, is the energy available to do something, to move a car, build a protein, drive a reaction. This is the energy available that we can harness. And so, as we recall, in order for delta G to be spontaneous, so a reaction is spontaneous, meaning it will happen when delta G is less than 0 or negative. And so the other thing we can use this delta G value for is if we have a non-spontaneous reaction. So for a non-spontaneous reaction, and that means, in other words, we have a delta G greater than 0. The delta G value we get, the energy that is positive, this tells us the minimum amount of energy needed to force that reaction to happen. So the minimum amount of energy required to force the reaction. To occur. Right? So when we have a spontaneous reaction, the negative delta G is telling us how much of it energy is available to do something. And if we have a non-spontaneous reaction, that positive delta G is telling us how much energy we have to put in to actually force that non-spontaneous reaction to flip it around, and so it goes spontaneous. We can look at some examples of this, and let's start off and look at an example where we look at the combustion of sugar. And so what we have here is a balanced chemical reaction that shows the combustion of glucose. So we have a sugar molecule, glucose, C6H12O6, reacting in the presence of oxygen gas to produce carbon dioxide and water. Glucose, or sugar, is one of the primary fuels used by our bodies, and this process of converting glucose into carbon dioxide and water, we can do in a vessel in the lab. We can burn it, and that's a combustion reaction, and this is also going to produce energy, as we'll see. Or we can do it in our bodies, where our body takes that glucose and metabolizes it. And while those two pathways are very different, in the end, we end up in the same spot of having carbon dioxide and water as the product and releasing energy. And so, because it's a state function, we can actually calculate how much energy is released. So when we look at this reaction, we might first want to say, what is the delta G of reaction for this process? All right, so what is delta G? And to find that, we can look up some Gibbs free energy of formation values from the appendix of your textbook or online, and we can see what I've done is pulled these data. So for every molecule in our reactants and products, we've looked up what is their delta G value. And just like with our other thermodynamic values, the delta G of reaction can be found by finding the sum of all of your delta G of the products and then subtracting the sum of all the delta G of our reactants. Okay. And so for this, we're just going to find our values. So delta G of reaction is going to be equal to our products first. And don't forget your coefficients. So we have carbon dioxide, but we have 6 times our value of carbon dioxide, which is negative 394.4, plus 6 times our water, negative 237.2. And then we're going to subtract our reactants, where we have our glucose. There's just one of those, so we have negative 910.1, plus 6 times our oxygen. We can see our oxygen is 0, so this is going to be plus 0. And you can take a second and pause the video and calculate this on your own. And we should get a delta G of reaction equal to negative 2,879, and I'll put my units back in, kilojoules per mole. So this is our delta G value. A couple things to take note of here. One is that this is a large and negative delta G. So this reaction is spontaneous, and this negative 2879 is the amount of energy that we can use to do something. So if we're burning sugar, we can use that energy maybe to turn a turbine and produce electricity to power a car. This is the energy available to our bodies to sort of harness in other ways. So if we think about our bodies can harness this energy when we go through this metabolism, can harness this energy. And one of the things we'll see is we can take a reaction like this and we can use this to drive other reactions that are non-spontaneous. So to drive a non-spontaneous reaction. But one of the things to keep in mind, or a couple of things to keep in mind for this is, first, nothing is 100% efficient. And what we mean by that is, while the combustion of glucose is going to produce this amount of energy, turns out we can't use all of that energy. A lot of the energy is going to be lost as heat. So we won't be able to use that full value, but we'll use a portion of that value. And some energy is going to be lost as heat. The other thing we can think about is, if you think about photosynthesis for a second. Photosynthesis, if we come back up here to our reaction, is just the reverse of this reaction, right? Where plants are taking carbon dioxide and water, and they're able to produce sugar and release oxygen in the process. So when we think about what photosynthesis is, it's the reverse of this process, which means photosynthesis has a delta G that is greater than 0. And in fact, what is delta G? Delta G for photosynthesis is positive 2879 kilojoules per mole. So how do plants overcome this? So plants, what do they use? Use sunlight. So they're able to harness the sunlight and use that energy from the sun in order to drive this reaction, right? Because they have to overcome the positive 2879 kilojoules per mole. And by using the sunlight, that's the energy source they can use to drive that chemical reaction.